Okay, so in C and C++, we can have a type called a pointer. And a pointer would be declared like this. Int. Now, here's the difference between a pointer and a regular variable. We could say star, and I'll use the letter P, the first letter of the word pointer. What does this mean now? What this means is, and I'll draw our storage in a different color. Right, now let's say, for example, let's say we do this. Int I equals 5. What has happened? We have a piece of storage somewhere in our address space. The operating system gave us some storage. And we were given a piece of storage for however big an integer is. Remember how many bits an integer was in the other class? Okay, well, it doesn't matter for this class. We get a chunk of storage, and let's say this is it. This is 5. We store a 5 in there. It's actually stored in binary, but I'm just writing in decimal, so it's easy for us to remember. Let's say we are at memory location, I'm going to make it simple, let's say 1,000. And this is 1,001, 1,002, 1,003, and so on. Right, our memory is some kind of order to it. The operating system grabbed us the next piece of free storage to store our 5 in. And int is another name. Int is now this location. I'm sorry, I is this location. So as far as our program is concerned, anytime we use this variable I, we're referring to this piece of storage. What we are allowed to do is create another type of variable called a pointer to an integer. Okay, what does that mean? We're going to get a separate piece of storage, and what will its contents be? We'll get a separate piece of storage, and its contents will be the machine address of some other piece of storage. So for example, if the operating system gave us this location to be where we store P, and I say, okay, so right now P isn't assigned to anything. Suppose now in my code I said, well, let me do this. Let me assign this. Hold on. Let me do this instead. P, so what this is saying is that P is not an integer. We don't store integers into it, but we store the address of integers into this location. If later on we wanted to say, I would like the contents of P to be 1003, meaning the address in memory of some other piece of storage, I could do the following. I could say P equals, and this is the ampersand symbol to say the address of I. And what this line would do is do exactly this.
So you only need the star when you're declaring it?
Right. When you're declaring it, the symbol star means this is a pointer to. So we could actually do this. And this gets a little, we could say this. This type is a pointer to an integer, and P is one of those. Or we could actually say it's an integer and put the star next to the variable. The thing this is just a side, that's actually a good point to bring up. This is a side, this is like a trick question in C and C++. What does this mean? X, Y, Z. And unfortunately, what this means is the first item, X, is a pointer to an integer, and Y and Z are actually integers. It's exactly the same as saying this. So the type is integer, the first one is a pointer to an integer, and the last two are actual integers. It's an annoying trick question, so unfortunately, if you want to make many pointers in one line, you have to put the star next to each one. So it's just generally safer to put the star over to this side, but it could have been either way. Okay, so what we've now done is we have a pointer, and its value is equal to the address of I. We didn't want to put a 5 in here, we wanted to put the address of I, which, now, if you wrote a program and compiled it like this, and ran it, and printed out the value of P, today it might print out 1003, and tomorrow it might print out 2005. It's whatever the operating system happens to give you as storage. But it will be whatever the address of the storage is that your program is currently running. So this seems like a pretty straightforward concept, but we can actually use these pointers to do some interesting things. Do you see any value to having these pointers? Anything right off the top of your head? Okay. So, if, so let's see, suppose we wanted, like one value to doing this would be if you had a really large object, not something small like an integer, but if you had a really large object. And let's say, well, this will make sense later on down the road when we talk about classes, but you could create a class or a structure for a person with a first name and a last name and age and a whole bunch of fields. And you could have them all listed in an array, and then you might decide you want to sort them. Well, it could be very painful if they're very large and you run a sorting algorithm, you start swapping storage around. It might be better to just create a bunch of pointers to them, and then every time you decide one's smaller than the other, you just swap the pointers. Okay. So, what you'll typically, when you look in most textbooks, it won't draw out the storage like this. I want you to kind of just see what the storage might look like. But what you might see in a textbook, looking at code like this, if somebody gave you this code and said, draw a picture of the storage, this is more likely that's what you'll see. You'll see a box called I, which has the contents of 5, and then you'll see another field for the pointer, and there'll be a little arrow that goes like this. You'll almost always see that in a textbook. What this is really saying is, we have a variable called I. So a variable is a piece of storage that has an initial name assigned to it. Its contents are 5. And then apparently we have a pointer whose contents is the address of 5. So now what if we didn't have I, but we had P, and we wanted to print out the contents of 5? What do you think would be the symbol for doing that? So if we did printf, and we only have P, if we wanted to say, we want to print out 5. So for example, if we said this, if we said printf, if we said P, it would print out, in this case, 1003, the contents of P. What if we want to say, I don't want to print out P, I want to print out the thing being pointed to by P. I want to print out the 5. What would we have to do? We'd have to put in some kind of symbol that says the thing pointed to by P, right?
Mm-hmm.
So if we said print F star P, that means the thing pointed to by P. So the output of this program would be, if you ran this, the output would be 103 and then a 5. And next class I'll actually write some program that uses stuff like this. So it's a very, very short program, but it gets right to the point.
So you put the star behind the P, it prints out the...
That means don't print P, look at the value of P, and then go to that spot and then print what's there. So go to...
That's the star means? Behind the P?
Right. So if something is a pointer, its contents will always be a memory location, part of the memory that your program got. That'll always, if it's a pointer to anything, it will always have some machine address to it. Even if, like, we can make a pointer to a person, and there'll be a big chunk of storage for a person, and then this will be the address of the very first part of it. So it's always the beginning of a piece of storage. So now if you say print P, that's gonna print the contents of P, 1003. If you say print the thing, star means take the address of P and go to that location and then print that thing. This will print to 5. Okay, so now, we'll just talk about arrays again. This actually makes it easy to follow what arrays are doing. And this is the way arrays are implemented. They're implemented with a pointer. Pretty much in any language, like Java, C#, C++. We could say, like, how is an array declared in any language you're comfortable with? An array would be something like this. An array of floats. Array, let's say array of floats. We would go like that. What does that mean? That means that we have 10, maybe I should make 10, we make it smaller. Make it 3 floats. What that means is somewhere in our storage, let's say this was now our array, 1, 2, and 3. So this right here is going to be our array AF, meaning array of floats. Okay. Okay, so as we're getting storage, generally the computer will give us the next piece of storage right after it. Sometimes there's fragmentation and it'll jump somewhere else to get a storage, but generally it comes out in a row. This line doesn't actually take up any more storage. All I did was said I want to put the value, I want to assign a 103 into this location. Now I'm declaring more storage. I'm saying, get me an array, the type is floats, and I want an array of them, size 3. And now I can do things like say, AF0 equals 2.5. AF1 equals 3.14. Let's say AF2 equals 2.71. Okay, something like that. What would end up happening? So what would end up happening is the variable AF is actually acting like a pointer to the beginning of your program. As a matter of fact, there'll be a piece of storage for AF. So let's say somewhere else, let's say this location happened to be free, we're going to use this as AF. Let's see, we'll do this. AF would actually be a pointer to where the array AF starts. So the AF would go something like this. So really what an array name is really a pointer to the beginning of the array. It is the machine location for the beginning of the array. And if we go to say AF0, I want to put something in location AF0. What we're really going to do is take AF and then add 0 to it. So AF would be 105, and then if we took 105 and added 0 to it, we're still at 105. So this line would do this. 2.5. If we then said AF1, we're actually taking the pointer to AF, which is 105, and then adding 1 to it, and that's this location. So we actually have a pointer to that location. And then this would do this. And this is actually how arrays are implemented in any language you've seen. Java, yeah, they all do this. The name of the array acts as a pointer to the array. And then the last line would do this. 2.71. Okay. Now, what if we did this? What would you think what would you like to have happen? What do you think should happen? If I'm declaring this array of size 3 spots. So one thing, just to, I know we talked about arrays before. It might be intuitive to think that if you have an array with 3 slots, the numbers of the slots would be 1, 2, and 3. But when you think of it as the array is actually, the array name is actually acting as a pointer, and you're adding this onto the pointer, it makes a little bit more sense to start at 0 and go to 2. But if I'd say that the array has 3 spots in it, and then I try to go right to the 4th spot, what would happen? What?
It would be outside the array, right?
Right, so what would you expect that would you assume the compiler would know it only goes up to 2, it goes 0, 1, and 2, and 3 is no good?
Well, in C++, you said no, right?
Yeah, so what ends up happening is, this could have been a variable, right? This could have been an I. Like, we could have had a for loop, right? That just, so this would not be 1, 2, 0, 1, 2, and 3. It could have been I, and I keeps changing. And the compiler can't tell what I is gonna be 20 minutes from now. You're running the program, and you might be getting values for I from the outside world. It won't know what I is. So the compiler can't say, well, the array only goes from 0 to 2, and 3 is out of bounds, because this could have been some variable. But if it went out of bounds, what would you want? What would you like to happen?
Just go to the next spot. Oh, on like make it 1008, right?
No, would you want this to happen?
No.
No, because this could actually be some other variable, right? Somebody could have declared,
I mean, but is that exactly what would happen in
And-
C++?
wait, so this could have been like int x equals 6, which would have had a 6 here. Right, this is now x. But then somebody came along and said the array location 3, which really isn't part of the array, equals 10.5, and now this would happen. And that might not be something you want, right? You might not want that to happen, because this array shouldn't be changing the value of x. This might not be what the people intended. So what would you like to have happen? Would you like to, at runtime, not during compile time, because the compiler can't figure out, like I said, this could have been, yeah, let me actually put this in. Let me make this an I. Yeah, let me change this to a 4. No, sorry, change this to a 3. And then I could have said AF sub I equals 10.5. I happens to be equal 3 at the time, but maybe along the code here I changed, it got multiplied by 2 and divided by, who knows what happened to it, and it somehow ended up 3. The compiler at compiler time can't track what I is going to be. So it's going to let it compile. It assumes you know what you're doing, and I is some legitimate value. But if this went out of bounds of the array, what would you, if you were designing the language back in 1972, what would you, what choice would you have? What would you do? Would you make it say,
Error.
You'd say error, and then your program must stop and throw an exception and kick it out and tell them start over? Or would you just let it go through? So when when C was originally created, it would just go right at it. It would just write to it. Now, if it was to be an error, there would have to be something going on at runtime that says, I know this array is only 3 large, and you're trying to write into the 4th spot, and that's no good. and I am now telling you there's an error. Well, if that were true, and that's a good idea, every time you ever try to write into an array, this check would have to be done. Well, let's see, you're trying to write into slot number 3, but the array only goes from 0 to 2, 3 is not allowed, you know, and then even when you want to write to a legitimate spot, like slot number 1, we still have to check that you went out of bounds on it, and that's gonna take some time. So now every time you, even though it's a good idea to check before you go right to it, it's now gonna make your program run time consuming. So in C++ and Java, in C and C++, you can actually go out of bounds, and I'll go over an example like that next class. Java came along and said, let's slow it down and do a check every time to see if you're within bounds, and
But if you had to do
It's
your own
safe.
check in C, right, you'd have to do like a while loop kind of in a sense to make your own check.
right,
if
and what you might want to do, and this is so when C came along, and we could have methods that are actually tied to the array, and we could rewrite the method that assigns to an array, and we could put our own check in if we wanted to, if we wanted to be safer. So it's the opportunity to be safer was there, with C and C++, with object-oriented programming. What that basically says, like in C, right now, any array you declare is open to the public, anybody can write on it from anywhere in the program, and they could actually use the pointer to it to write to even spots that aren't even part of it.
So there aren't public and private in C.
Right, so public and private is a C++ and all languages after that concept. And you're starting to realize why it's important to have that. It might be nice to declare an array and say, I don't want anybody using it except for me, and I'll give you methods on how to use it. And then you can add your own stuff, like I'll check that the place you're writing to is actually in bounds, and I'll tell you you have an error, or I'll handle it the way I want, rather than just have the storage just be a free-for-all for the whole program to use.
And can you really mess up your computer by like assigning something that you weren't supposed to assign? Like,
Well, your storage, the operating system will give you a chunk of storage for your program. So you could write all over that and not hurt anything outside of your program. But you could also try to write out of bounds of your program, and then you'll get some exceptions saying you've gone too far. So you could still get that in C and C++, with C and C++. But Java would never let you write outside of,
but for C, you can write outside of your program.
yeah.
So potentially you can really mess something up.
Yeah, so you could actually create a pointer that points to the location 0, and your operating system is in location 0. If you then try to write to it, you're gonna get an exception saying you're trying to overwrite the operating system, so.
But in C, it's just gonna be like, woohoo.
Well, no, in that case, if you try to write to a location outside of your address space, you're gonna get an error. The operating system won't allow you to write outside of your address space. But if you try to write anywhere inside your address space, it's wide open. It's the wild, wild west. You can write anywhere. Okay, so, let's see. Now, in C and C++, there's also a concept called references. So there's a third type of storage location. And, let me just do one thing while we're on the topic of arrays. I could do this. I could create a pointer, and the pointer will point to if I have an array like AF, I could say float pointer FP, float pointer, equals AF. Now what have I done? I've created a new piece of storage, which is a float pointer. Its contents is the beginning of the array. So this would also be 1005. So this is now a separate pointer, 1005. But now what I can do is, I could say now FP plus plus. Which is, as you remember, plus plus is the same as doing this. And what that would do is do this. Now, one thing, just as a side, I'm using kind of a shortcut with these numbers, because I want to illustrate the point. I think it's easy to follow the point this way. These memory locations generally are in sets of like 32 bits, and so the number might be, these numbers are like maybe 32 bits apart, or 4 characters each, or something like that. And when we say I want to add 1 to a floating point pointer, it's whatever the size of the object is. So let's say a floating point is 32 bits, and I want to add 1, I'll go 32 bits later. It's like 1 unit of 32 bits later. If this ended up being a pointer to something huge, like a person object, then, let's say that was 100 characters long, and I wanted to go 1 more, then I would go 100 characters later. So it means 1 more of whatever these things are. So I'm oversimplifying it by saying everything's 1 away. But, yeah?
Why wouldn't, when you make the pointer FP, why wouldn't it point to the location where AF is? Because...
that's a good question. This is a confusing thing. What you're saying is, why didn't this say 1,000?
Yeah.
Right? Why didn't this say 1,000? Because what we're saying is, or maybe, why didn't I have to put the ampersand here? Either way, and this is actually the one exception where you don't have to do that. If it's an array name, this thing is actually never used. It's always meaning the actual array. So this is the one exception where you could just say it by its array name, and it will actually give you the contents of it. It'll actually give you the address of the thing being pointed to, so it goes 1 extra hop. But that's a good question, and I almost wish they didn't change that. So, so one more thing was, we can add 1 to this pointer. Now the question is, if you were designing the language, would you allow this? This is the actual name of the array. Would you allow this to happen? And I guess what that would end up doing is this. Would you want that? So obviously you're giving more freedom to people, but do you see an inherent danger to doing that? So what we've done is we've declared an array. The array name actually acts as a pointer to the beginning of the array. Would you want to be able to move that pointer around, or do you want to have a rule that says all array names, all those pointers must be frozen?
Probably frozen.
And what's the danger? Obviously, the more flexibility, the more stuff programmers can do. But what's the danger of moving it around?
Goes to the wrong place.
Yeah, but if it moved, like let's say the size is 3, if we moved it, it's moving the array with us. It almost doesn't make sense to move an array around. Right? Because unless it's somehow new to shrink it, and then you're losing the beginning of the array, and then if you ever came back, you would grow the array back. So if the array is of size 3, and you wanted to even write in some check, make sure that I'm not writing to more than 3 spots at once, if we started moving the array around, we'd have problems. So they've decided to there's a special type of pointer. And this is also something we'll just come up when we talk about declaring storage in classes. There's a type of pointer called, or a type of variable field called constant. So that ever come up in any other programming class, a constant field? So you could say this, constants. So not only does did constant ever come up in any of your other classes? For variables, say this will never change?
Final?
Okay, yeah, right. Okay, so in Java it's final, and in C++ it ends up being constant. Okay. So what this ends up meaning is not only is this a pointer, but it's a pointer and it will never change from this moment on. It's constant. So array names actually are not just pointers, they don't act as pointers, they actually act as constant pointers. So they take on an original value, and from that moment on, they never move. So if you wanted to have a pointer to keep moving up and down, let's say you had some program that, let's say you had an array of 100 things, and you wanted to be able to walk up and down searching for stuff, you couldn't keep updating the name of the array, but you could create another pointer and then have the pointer go +1, -1, and move all around. So it gives you a lot of freedom to have something like this. So this would be an error. That would not happen. Okay. So there's one other type. So right now we have two types of storage we've talked about. We can declare a variable, like I. That means we get a chunk of storage, and we can write to that variable. We can also have a pointer field. That's a separate piece of storage, but its contents is the address of where another piece of storage is. And then there's a third concept in C and C++ called a reference. And we can go like this, integer, and then we'll do this ampersand. We'll do these ampersands pretty good. R. I'm using the letter R for reference. So R, now, what does that mean? And if you know Java and C++, this might be a little confusing. This is a reference to some piece of storage that already exists somewhere. In Java or C Sharp, you can declare a reference and then assign it later on. You can't do that here. What we could do is we could go like this. And what does that do? That just means R is another name for the piece of storage that I is on. So now, if we said R equals 7, then this would happen. R is just another piece, another name. R is now a reference to some piece of storage, but the R will never move around. So, for example, if we had, let's say we had R, another integer reference, R2 equals, we don't have anywhere else to put it, let's say I2. We had a second I. So we might have a second piece of storage called I2. Let's say we had I2 over here. Now R2 is another name for it. And I2 equals 4. Now we could say, so we said reference R2. So a reference is just another name for some already existing piece of storage. And let's say we decided to have R2 now equal something else. Suppose we decided to have R2 equal R1. What would that do? Now, if you're familiar with Java and C Sharp, it's going to do something different than what you're used to. What's going to happen here is the contents of R1, whatever R1 is referring to. Wait, is there an R1? No, it's just an R, sorry. Okay, the contents of what R is referring to, which is a 7, will get copied over to what R2 is referring to, which is this location. So this 7 would get copied over here. So these references, once they come alive, so they're just like variables, when you hit the open paren and close paren, is when they come alive and die. Once they come alive, they must be initially assigned to some piece of storage, and then it stays there while it's alive. Okay. So does that make sense? And it's probably more confusing if you know a language like C# or Java, which has references that can actually move around. These references in C++, they get initially assigned to a piece of storage and then stay there for the lifetime of that variable. Okay, so now, what would happen if, let me erase the storage, if we had a function like swap? Suppose we wrote a function that'll take two really objects of any type and swap them. Suppose we had a function, remember functions or methods, suppose we had a function like this. Which takes in an integer x and an integer y. Okay, as input. And what does it do? It says integer 10 equals x, integer x equals y, and integer sorry to declare x equals y, y equals 10. What would happen? Okay, so that's a function or method somewhere in our code, and then somebody comes along and does this. And then goes to print them out. So whatever your favorite flavor of print is, in C, it's print out. And B. Would you expect 3, 2 to get printed out? So obviously the goal of this routine here, swap, takes, you give it 2 variables and it moves them. That's what its hope is. It's trying to swap the 2 variables. So if an A is 2 and B is 3, and then you call swap, hopefully A is now 3 and B is 2. This thing got a temporary variable, copied some field over, and then, so let's just trace what happens. Here's our main program, and then here's this side function. So let's draw our story. We have a variable called A, which contains a 2. We have a variable B. I'm not drawing these in a row like I did before, but we have a variable B which contains a 3. Now we call swap. We pass in these 2 variables. What does that mean? What is x and y? Are x and y another name for an already existing piece of storage? Or does this function create 2 new pieces of storage, x and y, and fill them in with data?
New pieces?
New pieces of storage, right? Because for a very simple reason, and in C and C++ it's explicit. We didn't put an ampersand here to say that this is a label for someone else's piece of storage. This is obviously a brand new piece of storage. So we get a new piece of storage, x, and a new piece of storage, y. We can explicitly say, no, this is not a new piece of storage, it's put this label on someone else's storage. We can explicitly do that. Okay, so now what happens? The value of A gets copied into X, right? And the value of B gets copied into Y. So this happens. 2, 3. Okay, now what happens? We create a brand new variable called temp. 10. And what do we do with temp? We put a 2 into temp, right? We take the contents of X and write it into temp. So we go like that. Then we take the contents of Y and write it into X. Then we take the contents of temp and write it into Y. Right? Looks like the swap's working so far, right? And then we hit the close paren, and what does that do? Does this. And we're done. Right? Is that what we wanted? I mean, yeah, we copied the values over to these parameters, X and Y, and we successfully swapped the two values, but then we didn't do anything about it. We
It
didn't,
doesn't assign them to A and B. Is that what you mean?
yeah, what? Because then we're not saying that we're assigning them to A and B. We just copied them all over somewhere else, swapped some values around and went away. Nothing came back. So, does that make sense that nothing would come back? Well, it's not what we wanted, right? Obviously what we wanted is somehow those swap values to come back. But they didn't come back. So is there any, and actually this would happen in Java or C++ too, they wouldn't get swapped, even though it looks like you're trying to swap. How could we make them get swapped? Using like references or pointers. What? Like for example, what if we made what if we made X and Y, instead of being its own piece of storage, what if we just made it another name for someone else's store? So what if we did this?
So then X would be referring to A.
Right. Right, so what our goal is to have X referring to A. So we're receiving them as references, and what would we have to pass into them? So like for example, we had before, we had a reference, R was equal to some already existing variable. So we could do the same thing here. We could actually pass in pointers, objects being pointed at, or we could pass in fields just like this, A and B. So now what would end up happening is that X and Y would be another name for these fields. So X and Y would not be new pieces of storage, but instead they would just be labels for already existing pieces of storage. And because they are being assigned as soon as they get created, they know exactly what they are labels to, then what we can do is we'd have a field called temp. We'd have a field called temp, that's a separate brand new piece of storage. So now temp would be X, which is 2, and X is just another name for A. And then Y, which is another name for B, would become 3. And then, I'm sorry, this was what, 2 and 3. X would become Y's value, so 3 would get written here. And then Y would become whatever temp is, so 2 would get written here. And then the program would end and this would go away. And now we've actually swapped the values. And then, is there another way we could have done this with pointers? Right, so it's just, I guess that's just something we could think about going forward. But what we wanna do is not actually have brand-new temporary storage, have stuff copied over, and then only play around with the temporary storage, and have nothing get written back to the parameters that are coming in. If we could somehow associate the two pieces of storage to say X and A are exactly the same thing, they should refer to the same thing. So if we passed in a pointer pointing at A to some field here, and then used it as a pointer here, any updates would actually be pointing to the same piece of storage. So we could have done the swap using pointers or references. Okay, and then just in case you've read other languages like Java and C++, Java and C Sharp. Java and C Sharp got rid of the idea of using pointers, and everything is a reference in Java and C Sharp. Everything except for what you refer to as the primitive types, like integer and float. They're just like C and C++ in that you get a piece of storage and that's its name. But any object you ever create in Java or C Sharp, you create a reference, and that doesn't actually cause the thing to get created. The storage that gets created, you have to actually call new to have it created, and then say the reference equals the thing that came back from new. Okay. Is there any question about this?